For centuries, our understanding of the physical world has relied on rigid rules. We use classical geometry to define reality, calculating exact lengths, measuring precise angles, and plotting distances to make sense of our surroundings. But the natural world rarely fits into straight lines or perfect circles. Look inside the nucleus of a human cell. There, you will find a strand of DNA folded and tangled into a complex knot. Standard measurements are difficult to apply here. Whether that DNA strand is stretched out flat or bunched into a tight ball, its biological function remains the same. Or consider a robot navigating a cluttered warehouse. It doesn't actually require a millimeter-accurate map of every box. It only needs to know if a continuous, unbroken path exists between its current position and the exit. To analyze these flexible systems, we need a mathematical framework that looks past the specifics of size, shape, and distance. When we stop prioritizing rigid measurement, we arrive at topology, a field often described as the geometry of the rubber sheet. Topology studies the properties of geometric figures that remain the same even when stretched or bent. This is defined by a concept called homeomorphism. Two objects are homeomorphic if you can continuously deform one into the other without tearing the material or gluing pieces together. This leads to a classic observation. A topologist views a coffee mug and a donut as the same thing. If that mug were made of clay, it could be reshaped into a torus, where the handle naturally becomes the center hole. Because nothing tears, they share a genus of one. No matter how stretched, that single hole remains a structural rule. In contrast, a solid sphere and a torus can never be identical. The sphere has a genus of 0. To create a hole in that solid ball, you would eventually have to tear the material, violating the rules of continuous deformation. We also look at connectivity. This measures whether a space is a single, whole piece, or if it is separated into distinct parts. A continuous line is connected, regardless of how long it is or how it's coiled. When the details of exact shape and size are removed, these persistent structural properties are all that remain. Following these rules reveals objects that challenge our intuition. Take a Mobius strip, for example. Because of a single half-twist in the loop, the strip possesses only one side and one edge. If you trace its surface, you will cover the entire object without ever crossing an edge. There is also the Klein bottle, a surface with no defined inside or outside. In our three-dimensional world, its neck must pass through its own side, but mathematically it exists without any self-intersection in 4 dimensions. These rules scale into massive branches of mathematics. General topology provides the foundation, using collections of points called open sets to define continuity without needing to measure physical distance. Algebraic topology takes it further, applying algebraic structures to help distinguish between spaces that might look similar but have different internal connections. Geometric and differential topology focus on specific dimensions and manifolds. This is where topological rules are linked to the precise calculations used in calculus. These tools solve major problems. For over a century, the Poincaré conjecture regarding the nature of three-dimensional spheres stood as a legendary challenge. It was finally solved in the early 2000s by Grigori Perelman, using the methods of differential topology. Perelman's work demonstrated how topological methods provide a rigorous way to classify three-dimensional spaces, moving these concepts into the center of spatial analysis. But the question remains, why do these rubber sheet rules apply to the physical universe? It's because many systems rely on arrangement rather than measurement. In molecular biology, scientists map the knots and links in DNA to understand how the strands coil and replicate during cell division. We see this in data science. Messy datasets often look like random noise, but through topological data analysis, or TDA, we filter that noise to reveal a distinct shape, like this loop. TDA ignores the exact value of every single point. Instead, it looks for underlying connections to identify patterns standard statistical methods miss. In advanced physics, topology dictates how certain quantum phases of matter behave and provides the mathematical language for the dimensions explored in string theory. In these systems, the topological arrangement determines the outcome long before the specific measurements of length or angle come into play. To understand a truly complex system, we have to look past the superficial surface. Topology provides a way to ignore the noise of measurement and focus on the spatial properties that actually endure through constant change.